In mathematics, an order topology is a certain topology that can be defined on any totally ordered set. It is a natural generalization of the topology of the real numbers to arbitrary totally ordered sets. If X is a totally ordered set, the order topology on X is generated by the subbase of open rays for all A, B and X. This is equivalent to saying that the open intervals together with the above rays form a base for the order topology. The open sets in X are the sets that are a union of such open intervals and rays. The order topology makes X into a completely normal Hausdorff space. The standard topologies on R, Q, and N are the order topologies. Induced order topology. If Y is a subset of X, then Y inherits a total order from X. The set Y therefore has an order topology, the induced order topology. As a subset of X, Y also has a subspace topology. The subspace topology is always at least as fine as the induced order topology, but they are not in general the same. For example, consider the subset Y equals -1, 1, n, n, n in the rationals. Under the subspace topology, the singleton set -1 is open in Y, but under the induced order topology, any open set containing -1 must contain all but finitely many members of the space. An example of a subspace of a linearly ordered space whose topology is not an order topology. Though the subspace topology of Y equals -1, 1, n, n, n in the section above is shown to be not generated by the induced order on Y, it is nonetheless an order topology on Y. Indeed, in the subspace topology every point is isolated. So the subspace topology is the discrete topology on Y, and the discrete topology on any set is an order topology. To define a total order on Y that generates the discrete topology on Y, simply modify the induced order on Y by defining -1 to be the greatest element of Y and otherwise keeping the same order for the other points. So that in this new order we have 1, n less than 1 to 1 for all n, n. Then, in the order topology on Y generated by less than 1, every point of Y is isolated in Y. We wish to define here a subset Z of a linearly ordered topological space X such that no total order on Z generates the subspace topology on Z, so that the subspace topology will not be an order topology even though it is the subspace topology of a space whose topology is an order topology. Let in the real line. The same argument as before shows that the subspace topology on Z is not equal to the induced order topology on Z, but one can show that the subspace topology on Z cannot be equal to any order topology on Z. An argument follows. Suppose by way of contradiction that there is some strict total order less than on Z such that the order topology generated by less than is equal to the subspace topology on Z. In the following, interval notation should be interpreted relative to the less than relation. Also, if A and B are sets, A less than B shall mean that A less than B for each are in A and B in B. Let M equals Z minus 1, the unit interval. M is connected. If M, n, M and M less than -1 less than n, then and separate M, a contradiction. Thus, M less than -1 or -1 less than M. Assume without loss a generality that -1 less than M. Since -1 is open in Z, there is some point P in M such that the interval is empty. Since -1 less than M, -1 is the only element of Z that is less than P, so P is the minimum of M. Then MP equals AB, where A and B are open and disjoint connected subsets of M. By connectedness, no point of ZB can lie between two points of B, and no point of ZA can lie between two points of A. Therefore, either A less than B or B less than A. Assume without loss a generality that A less than B. If A is any point in A, then P less than or in A, then equals P A, so P A is open. P A equals P A, so P A is an open subset of M, and hence M equals B is the union of two disjoint open subsets of M, so M is not connected. A contradiction. A space whose topology is an ordered topology is called a linearly ordered topological space, and a subspace of a linearly ordered topological space is called a generalized ordered space. Thus the example Z above is an example of a Go space that is not a linearly ordered topological space. Left and right order topologies. Several variants of the order topology can be given. The right-order topology on X is the topology whose open sets consist of intervals of the form. The left-order topology on X is the topology whose open sets consist of intervals of the form. The left and right-order topologies can be used to give counterexamples in general topology. For example, the left or right-order topology on a bounded set provides an example of a compact space that is not Hausdorff. The left-order topology is the standard topology used for many set-theoretic purposes on a Boolean algebra. Ordinal space. For any ordinal number lambda, one can consider the spaces of ordinal numbers together with the natural order topology. These spaces are called ordinal spaces, and lambda plus 1 equals 0, lambda. Obviously, these spaces are mostly of interest when lambda is an infinite ordinal. Otherwise, the order topology is simply the discrete topology. When lambda equals omega, the space 0, omega, is just n with the usual topology, while 0, omega, is the one-point compactification of n. Of particular interest is the case when lambda equals omega 1, the set of all countable ordinals, and the first uncountable ordinal. The element omega 1 is a limit point of the subset 0, omega 1, even though no sequence of elements in 0, omega 1, has the element omega 1 as its limit. In particular, 0, omega 1, is not first countable. The subspace 0, omega 1, is first countable. However, since the only point without a countable local base is omega 1, some further properties include neither 0, omega 1, or 0, omega 1, is separable or second countable. 0, omega 1, is compact while 0, omega 1, is sequentially compact and countably compact, but not compact or paracompact. Topology and ordinals. Ordinals as topological spaces. Any ordinal number can be made into a topological space by endowing it with the order topology. In the absence of indication to the contrary, it is always that order topology that is meant when an ordinal is thought of as a topological space. The set of limit points of an ordinal alpha is precisely the set of limit ordinals less than alpha. Successor ordinals less than alpha are isolated points in alpha. In particular, the finite ordinals and omega are discrete topological spaces, and no ordinal beyond that is discrete. The ordinal alpha is compact as a topological space if and only if alpha is a successor ordinal. The closed sets of a limit ordinal alpha are just the closed sets in the sense that we have already defined, namely, those that contain a limit ordinal whenever they contain all sufficiently large ordinals below it. Any ordinal is, of course, an open subset of any further ordinal. We can also define the topology on the ordinals in the following inductive way. 0 is the empty topological space. Alpha plus 1 is obtained by taking the one-point compactification of alpha, and for delta a limit ordinal. Delta is equipped with the inductive limit topology. Note that if alpha is a successor ordinal, then alpha is compact, in which case its one-point compactification alpha plus 1 is the disjoint union of alpha and a point. As topological spaces, all the ordinals are Hausdorff and even normal. They are also totally disconnected, scattered, zero-dimensional as the union of the Clopin intervals equals beta plus 1, gamma, for gamma, less than gamma. However, they are not extremely disconnected in general. The topological spaces omega 1 and its successor omega 1 plus 1 are frequently used as textbook examples of non-countable topological spaces. For example, in the topological space omega 1 plus 1, the element omega 1 is in the closure of the subset omega 1, even though no sequence of elements in omega 1 has the element omega 1 as its limit. An element in omega 1 is a countable set. For any sequence of such sets, the union of these sets is the union of countably many countable sets. So still countable, this union is an upper bound of the elements of the sequence, and therefore of the limit of the sequence, if it has one. The space omega 1 is first countable, but not second countable, and omega 1 plus 1 has neither of these two properties, despite being compact. It is also worthy of note that any continuous function from omega 1 to R is eventually constant. So the Stonecheck compactification of omega 1 is omega 1 plus 1, just as its one-point compactification. Ordinal indexed sequences. If alpha is a limit ordinal and X is a set, an alpha indexed sequence of elements of X merely means a function from alpha to X. This concept, a transfinite sequence or ordinal indexed sequence, is a generalization of the concept of a sequence. An ordinary sequence corresponds to the case alpha equals omega. If X is a topological space, we say that an alpha-indexed sequence of elements of X converges to a limit X when it converges as a net. In other words, when given any neighborhood U of X, there is an ordinal beta less than alpha such that X iota is in U for all iota beta. Ordinal indexed sequences are more powerful than ordinary sequences to determine limits in topology. For example, omega 1 is a limit point of omega 1 plus 1, and, indeed, it is the limit of the omega 1 index sequence which maps any ordinal less than omega 1 to itself. However, it is not the limit of any ordinary sequence in omega 1, since any such limit is less than or equal to the union of its elements, which is a countable union of countable sets, hence itself countable. However, ordinal indexed sequences are not powerful enough to replace nets in general.